Okay, good day. Let's proceed with chapter 2. And this is video number 1 of chapter 2. Chapter 2 is flexural design of reinforced rectangular concrete beams. Okay. So general design concepts, we have the so-called limit states. Ano ba yung limit states? It is defined as condition in which structures becomes unfit for service, meaning may collapse. Now, there we have two major categories of the limit states. Meron tayong ultimate limit states and serviceability. This is actually with respect to this rank. Kasi meron din tayong yung tinatawag na sa economy, because we say design is sound, as so-called sound design, and it is safe from limit state strength and serviceability, as well as it's economical also. So economical. So we call that sound design. So yung ultimate limit state is condition which makes structure unsafe due to collapse of parts of all of the structure. Ibig sabihin pwedeng part lang ng structure or yung buong structure itself. While serviceability limit states condition which makes structure unusable due to disruption of the function use of parts or the structure. So usually ito mga deflection ito. Now, limit state design is defined as a design procedure wherein the structure or structural members are arranged and proportions. So importante, arranged and proportion, such that no applicable limit state is reached when subject to all appropriate load. Okay, actually, mamaya gagawin natin yan. Kunin natin yung load with a different load combination. So, meron tayong design philosophies. It is defined as system of principles used for guidance and determining and providing acceptable level of safety against occurrence of limit states. Actually, kaya tayo naglalagay ng factor of safety. Yung factor of safety. Now, ano ba yung factor of safety? That is our allowance para or margin of safety. Margin of safety. Para hindi siya mag-collapse. Okay. Now, two most commonly used, we have ASD or the allowable strength design and then load and resistance factor design. So this is actually two bases of design philosophy that we have to use. Yung AESD or WSD, and we call it working stress design, and LRFD, load and resistance factor design. Meron din tayong other design philosophy. We have so-called plastic design or limit design. Now, AESD and LRFD differs primarily on how to provide adequate safety against the ultimate limit state procedure, but the serviceability limit state are generally critical. Ang ibig sabihin lang dito, pagdating dun sa strength limit, magkaiba yung basis nila for the factor of safety. However, AESD and LRFD is just the same with respect to serviceability limit state. So meron tayong topic dito, that is chapter 5, I think, serviceability. With respect to limit state, the structure of member is safe if its resistance is greater than the load effects. Actually, ito yung safety requirement natin. So generally, we designate the total strength resistance or strength against action effects based on geometry, structure, and material. S and Q, the stress resultant due to action. Ano ba yung mga actions? By the way, here, kailangan S must be greater or equal to Q. Hindi po pwedeng less than. Actually, ang kaparehas lang yan, yung VMN must be greater or equal to MU. And so, ano ba yung actions na nagiging base nito, MU na ito? So, we have, of course, change geometry and state of stress in structure. That is the definition of action. And these are the causes. We have loads, settlement or differential settlement, change in temperature, creep, and shrinkage. So I have already discussed regarding creep and shrinkage. So I repeat, creep is due to sustained load, and this is due to loss of absorbed water. Nasabi dito, in design, we can only compute, estimate probable S and Q. That is totoo kasi hindi talaga natin ma-exact yan. So estimate lang yan. But sabi dito, we must therefore provide against understrength and overload. Okay, sinabi ko na ito before sa chapter 1, yung understrength. Yan, actually, nag-understrength tayo, kaya naglalagay tayo ng P. Then ito naman na overload, this is the load factor. Load factor. Kung baga yung load, dinadagdagan natin, pero yung strength binabawasan. Okay, I have already discussed it. Now, in strength design method, gamit tayo ng phi, ano? So, I have already explained that. And we have notation here, Sn is nominal strength, phi is the strength reduction factor, and Sg is the required strength. Then dito, yung sinabi ko dito, load factor, it is designated as omega. So that is here. Then dito. So, meron naman ang notation dito. This is the type of load such as dead load, live load, earthquake, wind load, etc. Okay, ganun ba yan? Again, we have here, I will repeat again, reason for specifying load factors doubly. We have the magnitude may vary from the building codes and uncertainty in calculation of load effects. So, I remember that this is being repeated here. We also have the reasons for specifying resistance factor. Okay. So, nasabi ko na ito. I have already explained this in our chapter 1. So, importante lang na kung tayo nag-design, kailangan adaptive system na kailangan ito. Huwag ito, bawal ito. It is not allowed by ACI codes. Now, how do we design a structure? So, yung mga design na even doon sa chapter 1, before we derive, we will able to derive the formulas. Meron tayong mga assumptions yan. Okay, actually ito yung mga assumptions. Number 1, strain in concrete is the same as in reinforcing bars at the same level, provided that the bond between the steel and concrete is adequate. And this is for double reinforced na, kasi sa double reinforced, yung concrete, dito yung steel. So, dito sa natin, sa strain diagram. Okay. Ito yung sa epsilon S prime. Ngayon, siyempre may band yung concrete and steel. Ang strain ng concrete yan, and strain of steel will be the same. Strain in concrete is linearly proportional to the distance from the neutral axis. That is why our strain diagram is linear, straight, diba? strike yan. That is the strain concrete. The modulus of elasticity of all weights of steel is taken as ito pala yan, sa English, 29,000 or 29 million pounds per square inch, so that is 29,000 KSI. So yung E kapag English yung ES is equal to 29,000 times 10 KSI. Ayan. The modulus of elasticity of all grade steel is taken as Now ito, plane cross-section continue to be plane before and after bending. Okay. Ganito lang yung beam natin. So for example, we have this beam, then this is subject to load. Before load, yung cross-section natin remains plane. Kumbaga ganito. Kahit nag-bend na yan, ng gano'n, plain pa rin siya. Plain pa rin. Hindi siya na-destroy. That is one of the assumptions. Number 5, the tensile strength of concrete is stimulated. Okay, this is important. Kasi yung concrete tensile strength is only about 10% of its compressive strength. And mamaya meron akong sasabihin mga videos kung itong 10% of its compressive strength. We say that concrete is assumed to be non-effective. Kaya neglect natin. Before cracking, the entire cross-section is effective in resisting the external moment. So kung makikita nyo sa WS, first topic natin, sa behavior ng concrete to load, before cracking, di ba, ginagamit na natin sa gross. So number 6, the method of elastic analysis, assuming an ideal behavior at all levels of stress is not valid. At high stresses, non-elastic behavior is assumed, which is in close agreement with the actual behavior of concrete and steel. Number 7, at failure, the maximum extreme compression fiber is 1.00. For design strength, the shape of the compressive concrete stress distribution may be assumed to be rectangular, parabolic, or trapezoidal. Actually kasi meron tayong mga stress diagram na pwedeng parabolic, pwedeng trapezoidal, pwedeng rectangular. Ngayon, ang ginagamit natin yung rectangular, yung kay Whitney. Ang ibig sabihin. Ngayon, these are the strain limits for tension and tension control section. This is actually for NSAP 2015. Kasi sa 2010, wala tayong, di ba, sa 2001, we only have under-enforced and over-enforced. Wala tayong transition region. The design provisions for reinforced concrete members are based on the concepts of tension or compression control section. Both are defined in terms of the net tensile strain, or the NTS, which is designated as strain P. In the extreme tensile still abnormal strength. Moreover, the two conditions may be developed. We have the balance strain condition and the transition region. So these four conditions are defined as compression control section, those sections in which the net tensile strain in the extreme tension still at nominal strength is equal to or less than the compression controlled strain limit at the time when concrete in compression rates its assumed strain of 0.002. So sabay na lang. So 0.003. And for grade 60, that is actually F equal to KSI, the compression controlled strain limits is actually 0.002. So meron tayo mamaya ng 0.002. Then actually alam niyo na yung 0.005. Kaya lang, meron tayong idadagdag dyan ng 0.00 kasi nagdi-design na tayo. Then, tension control section, okay, 0.005. That's number 2. And ito, yung ano lang, 0.00 and the balance technician. So, generally, magkakaroon tayo ng 4 in NMEC 2001 at 2015. Compression control, tension control, transition region at saka yung balance strain. So, ganito lang naman yung illustration natin. Sinabi ko na sa inyo na ito. Kapag ka-balance compression control, our strain is 0.002 for grade 60. For other grades, we have it's equal to Fy over ES. So this is the same as 2001. And we have the 0.005 for the tension control kahit anong grade ng steel. Then we have the transition region. Makikita nyo that the transition region is 0.002 to 0.005, that is for high grade steel, that is for grade 60 KSI. And we have here actually Fy over ES. And okay, so that po yan para mas maintindihan ganito. So kung titignan nyo doon, we have Fy over ES is less than or equal to, then we have here 0.005. So actually this is strain in the steel lang. Ngayon ito, pinapalitan na natin na ng Fy. Then, i-multiply natin ng ES yung sa kabila. Bagay mo multiply na naman natin yung ES dyan. Then, that will give you 1,000. Okay. Yan. So, marunong natin ang 15. Okay. Now, ito makikita nyo dito in English. Ito yung mga value. Ito yung mga value. May makikita kayo ng 0.004. That is, napaka-importante daw for flexural member. For flexural member, we are not going to use 0.004. However, we are going to use 0.004 to 0.005, especially in design. Okay. Now, using the design strength of beam using ACI code actually, we have so-called WSD and USD. And why it is also reasonable to take up WSD. Now, bakit kailangan pa mag-WSD kahit mas nasabi obsolete na siya? Una kasi yung task to permits the design of reinforced concrete for highway bridges using WSD. Is up for sa DPWH sa codes. WD is used by some designers for proposing fluid containing structure. The ACI method for calculating the moment of inertia for deflection calculation requires some knowledge of walking stress design. Take up chapter number 5. And then yan yung deflection. And the design of stress concrete members based not only on string design method but also on elastic stress calculation at such. Pag kumuha kayo ng this is in your sa old curriculum, that is TE4. So meron ngayon yung mga grade E4, that is pre-stress concrete. So pre-stressed concrete, that is the other part. Kumbaga RC din siya kaya ng pre-stressed concrete. Okay. Now, sabi dito, structural safety and WC tests based on service load are calculated and compared with allowed stress using ratios nila. Ito ang ratio nila. Or kaya ito. Actually, sa WSD. Okay. Yung WSD, hindi yan ang mga lang natin. In USD, the structural safety approach considers uncertainty and load strength. And actually, that is the overload and understrength. Okay, this is the very reason. Okay. So ngayon ito, alam mo na ito na. yung three types of members based on the balance section, tension control, and proportion control. Yun, makikita nyo naman dito yung points. There is yung okay. Now, we're going to go back here. So, okay, I've already explained that. So, itong beam consideration. So, beam considerations for shorter beams, wherein there is 6 to 7.5 meter on span. The ratio D per B can be taken as 1.5 to 2. And for longer beams, the deep narrow section is selected. For mga deep beams, we have the deflection control. Okay, then we are going to refer the table with the thickness ratio. Mamaya makikita niyo. Mamaya na-isip. Pero lahat naman na nasa inisip, actually scanning price. Yeah. Then estimated beam weight, selection of bars, concrete cover, and minimum spacing of bars. Okay, since nag-design na tayo, kung sa investigation, hindi na tayo nag-consider ng mga concrete cover, then yung nag-select tayo ng bar, we always use AES in computation. Then this minimum spacing of bars. In design, importante na ito. Ito ngayon yung makikita ng diagram dito. So we have, for example, a 2-layer bar. The code specifies that itong horizontal spacing na ito, horizontal spacing of bars between bars clear should not be less than 1 inch, that is 25 mm, or the diameter of that bar, whichever is larger. So for example, ginamit natin ito is 28 mm. So ibig sabihin, kung 28 mm yan, against 25, ito magiging yan. That is the horizontal spacing. For vertical spacing between layer, 1 inch. Ngayon itong concrete cover na ito is around 1.5 inch. 1.5 inch, that is equal to 40 mm. However, in our illustration here, wala tayong nakalagay na stirrups. Okay, so kailangan i-consider. Actually, clear cover is from stirrups. Then, ito yung deflection control minimum width thickness ratio from NSCP. Especially when we are designing beams and slabs for deflections. So we have for simply supported, and we have this solid one-way slab or beams with one-way slab. We have L over 120, L over 20, L over 24 for 1 end continuous, L over 28, and cantilever L over 10. So both ends are continuous. Ibig sabihin continuous beam ito. One end continuous. So, ibig sabihin ito. One end is continuous. So, pwedeng parang overhanging beam. Slab. Pero this is for slab, this is for beam. For beam, L over 16, L over 18, okay. Actually, pwede natin gamitin ito to select the width thickness ratio ng beam. Ano ba yung width thickness ratio? That is B over the total depth. Total depth ratio. So yan, you are going to have that. And meron tayo dito ng other designation regarding the weight of concrete. And itong for our FY of 415 method is actually grade 60. Grade 60 yan eh. 60 KSM convert niya. Then we have to multiply that by 0.4 plus y over 7. Anyway, yung mga ganito, na mga dagdag na ganito, kailangan kapag ka nag-design ka na medyo kabisado nito. Kaya kapag ka nagtrabaho ka as designer, talagang papuntahin ka muna sa Bible natin, sa civil engineering, which is the NSCP. Now, we have here the minimum concrete cover or reinforcement space limitation. So, sabi dito, the minimum clear spacing between parallel bars in layers have been less than 20 or dB. Actually, nakita nyo ito. Sinabi ko kanina. For parallel reinforcement is placed in 2 layers, sila 25. Now, this is spirally reinforced or tied reinforced compression member. Ibig sabihin, column siya, yung post na. By the way, yung post, hindi natin kakabit ng post. Column siya. So, meron naman tayong 1.5 dB or less than 40 mm. That is the cover. Kasi place concrete and pre-stress. So, we have ito. Minimum concrete cover for concrete cast against permanently exposed to 8. So, 75 mm or that is equal to 3 inches. Sa mga ano yan, sa mga footings. Okay, sa footings. Okay, footings. Halimbawa, ito yung footings natin. Tapos, paril niya, dito. Ito yung level ng ground. Kailangan, since 8 ito, kailangan yung clear covering natin will be 3 inches, mas makapal siya. So, concrete exposed to 8 or ito, yung mga beams na talaga ito nasa labas. So, for mga bar from 20 mm to 3650 and 16 and below 40. Actually, ito yung nakikita niya. However, meron pa tayo dito concrete not exposed to weather and contact. Actually, yung mga beams and columns na nasa loob ng building. So, slabs wall joist for 42 mm to 58. Laki naman ito. Pero meron yan. Slabs or joist ay kasama yung joist. Ano ba yung joist? Parang building. Then walls. Yung walls na ito, mga shear walls. So, 40 mm din. Pero kung titingnan nyo, laki naman ang diameter. So, 36 and was smaller. Malaki na nga yung 36, so 20 mm. So, mga size slabs, paano ba yan? Kaya ano ba kung boost tayo ng beam? Ito yung anong slab namin, slab. Ito yung bottom ng slab. Yung maglalagay tayo ng reinforcement ng bar at top and bottom. Kailangan yung cover natin dito is 20 mm. Yung iba, anong ginagawa? Diba, after pouring, makikita mo yung baka lumalabas. Kasi hindi sila naglagay ng mga spaces. Malalaman nyo lang yan kapag mga engineer na kayo kung ano tawag ng mga spaces. For beams and columns, we have 40 and okay, ito naman omega. Okay. Now, miscellaneous design considerations. Lateral bracings and for deep beams. We have the lateral support. Lateral bracings for beam is not required closer than 50 times than least with dimension B of the compression flats. Alam niyo kung ano yung compression flats. Kung baga ito yung beam, nandito ang compression flats at is subject to positive moment. Nandito yung positive. For example, flats or yung flange sections here. For example, o kahit na dito, kahit na rectangular beam lang siya. So, ito yung beam. So, kailangan bilateral support. Halimbawa, papunta rin yung beam natin. Papunta rin yung beam natin. Papunta rin yung beam. Ngayon, meron tayong support dito. Yung lateral support, yung mga support sa punta dito. Yan. Kailangan yung lateral supports dyan kung meron tayong beam na focus din dito. Kaya po steel, mga ano yan, kung baga yung beam yan, kung steel meron tayong laterally directed supports dito. Yung spacing na yan dapat hindi siya lalagpas sa 50 times the width B dito. Ito width B. Yan ang ibig sabihin mo. If torsion is appreciable lateral support spacing shall be considered. So talaga, especially kapag torsion. So when we take it, shear and torsion. Number 2, skin reinforcement. Ito, ano yung tinatawag na skin reinforcement for deep beams. Ito yan. Halimbawa, ito yung reinforcement natin. Ito yung reinforcement natin. Meron pa tayong dinadagdag dito. Ito yung mga skin reinforcement. Ang purpose niya kasi para hindi mag-crack. So for a beam with effective depth greater than 1 meter, okay. So, ibig sabihin, ang minimum depth natin kapag ang depth ng beam natin is 1 meter and greater. Makapal na yung makapal na yung 1 meter. Imagine kayo ng beam na 1 meter, diba? So, kailangan ng skin reinforcement. Okay. Ngayon dito, ito yung derivations of beams questions natin. Meron na yun doon, diba? Basta ang tandaan nyo lang dito, hanggang sa equilibrium. Ang ginamit FY Y ibig sabihin nag-yield, kaya sabi ko doon, huwag mong gagamitin yung formula yan kapag ka over-reinforced. Kakamali sa'yo. So ito yung mga derivation of expressions. Then meron tayo dito, ito, again, itong CB na to is applicable to all section. Then lumabas itong value na ito from this derivation using ES equal to 200,000 megapascal. Okay? Then yung 0.003 is CU. Then, so we have actually, ito, yung ginagamit natin formula. So, pwede naman dito. For balance, for rectangular section only, to forget. Then, to determine row balance, we equate T, C to P, pero in terms of balance, kaya mabot tayo dito. Formulang row balance for rectangular section only. Okay, ngayon, ito yung explanation ko. Makikita niyo dito yung C natin. Anyway, this is singular reinforced ng pala ito. So, di ba nakalagay dito AESFS. Ngayon, AESFY if nag-yield. Ngayon, di ba nagdi-design na tayo? We cannot afford kasi code does not permit this to be to not yield. Kailangan pag nag-design tayo, sigurado mag-yield yan. Kaya doon sa double reinforce na sabi ko doon sa chapter 1 na palagi natin i-assume na FY na dito, hindi na tayo gagamit ng FS. Then again, these are the flexural requirement for beta 1. Ulitin natin. Beta 1, 30 megapascal, 2001. Okay, 1992, 2001. So, okay na yan. Andiyan yan sa handouts nyo. Okay. Then, ito yung sa 2010. Sa 2010, kasi ang pinagkaiba lang nito, ito kasi nakalagay dito, for 28 to 55 sa 2015. Dito sa 2010, basta 28, parang yung sa 2001 lang nandun. Ganun lang. Dito, papalitan lang natin ito ng 30. 2001 yan. Dito sa 28, nakalagay lang, basta greater than 28. Gagamitin mo na po. Dito, may gamit na sa dito, limit to 55. Ngayon, convert nyo ito sa KSI or PSI kung ilang PSI ito na limit. Usually ito, mga 55 megapascal pang high-rise building na yan. Okay. Ngayon, ano yung requirement ng code? Ang requirement ng code, kailangan yung minimum reinforcement ito. Yeah. Square root of FC prime over 4FY, and that is equal, or this will be greater than 1.4 over FY. Now, try nyo equate yan. So, di ba kay itong FY na ito, cancel out, gawin nyo ito equal muna, then square sign, lipat mo sa kabila, ulitin mo FC prime, kaya lang megapascal. Sa araw mga 31 point something megapascal, I think. I'm not sure, so just try it na. Ngayon itong 0.75 row balance, okay, it's important. Itong 0.75 row balance is the field requirement for designing beam. Pero this is not only for this is not only for rectangular. Itong formula na row balance na ito is for rectangular only. Ngayon pwede naman tayong kumuha ng row balance. Pero iba yung computation kapag other section. Pero yung 0.75 kasama yan. That is for NSCP 2001. Ngayon, pag 2015 code, wala nang nakalagay doon na 0.75. Iba na. Sasabihin ko na lang. Okay. Ngayon, kapag ka nag-design tayo, kapag ka we want to control the deflection, pwede na tayo mag-target o kaya mag-set na yung raw actual na gagamitin natin is around 5.05 of raw max. No? Ano yung raw max? 0.05 or is it at 0.5 ito? Hindi correct. 0.5 raw max or that is equal to 0.5 times 0.75 of raw balance. Multiply nyo yung 0.5 times 0.75. Or we can use this value. Actually, kung titignan nyo yan, ano ba yung omega? Rho F1 over FC prime. Now, okay. Ngayon, kung balik mo ito dito, FC prime over Fy and the target rho, actually we are looking here for the reinforcement index. Sabi ito, now this value of steel ratio when calculating the beam dimension in order to deflection not be excessive itong mga ano na ito. So, by the way, kapag ka nag-design tayo actually, pwede tayong maraming design computations or design ng beam. Pwede, halimbawa, pinadesign ka ng beam rectangular, hindi binigay yung B and D. So, B and D, ito yung pinakamahirap na nag-design. Walang given na dimension. So, kasi pwede kang gumawa ng makadesign ng beam with reinforcement and dimension B and H with the corresponding D. Na basta ang importante, yung limit states hindi ma-violate. Okay, so we have here the for rectangular section. This is the required tensile stress ratio, which should always be greater than rho minimum, greater than rho minimum but less than rho max. So we have here the load combinations. Okay, meron na ito? Meron na kayo ito. So, hindi ko na-explain yan. Now, sa 2001, ito yung makikita niya na load combination. Then, meron tayo ng 2010 and 2015. So, I will give you also a copy. Bigay ko ng video na ito. So, be familiar with these load combinations. Okay. Then, meron tayo ng strain reduction factor na 0.90, 0.90, 0.75, 0.70, 0.85, and 0.70. Ito, first year, 2001, 0.85, and 2015, that is 0.75. Okay? Pag nagkaroon na kayo ng NCP 2015, tingnan nyo dyan, that is 0.75. Okay? So, this is for 2010. Okay, andito pala yan. Makikita mo dito sa 2010, asaan? Yung shear torsion, 0.75. Tama? Ayan, 0.75. Yeah, the other, this is bearing, 0.65. Pag tinignan natin dito, yung bearing is 0.70. Diba? So, just compare this value here ng 2010 and 2001 and 2015. And then yan, kung makikita nyo dito, sa 2010, 2001, palaging 0.90 yan. But in 2010, meron na tayo ito, yung value na 0.90 at 0.90 or 0.65. Ngayon, pag meron kayong mga books na English, ito talaga yung ginagamit, So ngayon sa YouTube o kaya sa mga books na ngayon na reviewer, kinonvert na lang ito sa, kumbaga in terms of strain ito. Ngayon, kinonvert in terms of stress para mas madali. Para mas madali ang computation. So, okay. Now, balikan ko na yung natin. Balikan ko na yung ito. So, ito. Ayan yan. Ito yung So, explain ko nga ulit yan. Okay. So, ganito lang yan. Ang graph na yan ay nakaganyan. Kaganan. This is 0.65, 40, and we have 0.90. So, ito, pwede by linear interpolation o pwede naman na right hand proportion. So, nakalagay dito, this is 0.002 strength. And dito is 0.005. Okay. So, ang explanation ko dyan, ito, this is NSCP, NSCP. So, 2015. Kapag ka dito ka sa case na ito dito, pag dito sa region na ito dito, tension control siya. So, hindi siya over-enforced. Pag dito, over-enforced siya. Pero meron tayo ng transition region. Okay. This is strain, and this is free. Ngayon, kung titignan nyo, kapag ang pinag-usapan natin is strain, pag malaking strain, nag-yield talaga siya, mas lalaki yan. 0.002, dito is 0.65, ang compression control dito. Ngayon, kung titingnan nyo yung mga example natin ng low balance, hindi design tayo. So, kumbaga, sa vertical tayo, if this is the value of raw balance, pag below raw balance, ibig sabihin, under-enforced, pag ganun, over-enforced na sa NSCP 2001. Okay, 2001. Especially kapag rectangular, kahit hindi rectangular section. Ngayon, pag nag-design ka, kasi ibig sabihin ito, singly reinforced din ba ito dito? And dito, double reinforced na kapag ka nag-design ka. Kasi hindi pwedeng maging over-design over-reinforced, hindi pwede. Over-design, pwede ba lang over-design? Magkaiba kasi yung over-design sa over-reinforced. So, over-reinforced, hindi pwede kasi brittle siya. Kapag not DRB, over-reinforced, INSP at over-reinforced. DRB, okay lang yan. Pero over-reinforced, under-reinforced dito. Pag nag-design tayo, kung mag-over-reinforced na siya, mag-double-reinforced na tayo. Pero hindi na tayo paabot dito. Nagbibigay tayo ng allowance ng 0.75 raw balance. Kumbaga, kung ito yung natin, yung raw balance, sabihin mo ito sa apat, diba ito 0.25, 0.50, 0.75. Huwag na natin paabutin dun sa 0.75 sa raw balance. 75% pa lang ng raw balance, mag-double reinforce na tayo, magdagdag na tayo. Para sigurado natin na yung FS mag-yield. Para sigurado mag-yield yan. Kasi pag dito ka, pag pinapunta mo siya sa balance, pag pinaabot mo dito sa balance, yung kumbaga yung AES na ipoprovide mo is nasa AES balance na. Pwedeng later on, pag check mo, ay over-reinforced pa rin. Okay. So kasi itong raw balance, pwede sabihin mo AES balance din. AES balance. Kumbaga yung AES max natin, kumbaga pwede natin gawing 0.75 of AES balance. Actually, this is the general expression. Ngayon, gumagamit tayo ng raw max equals to 0.75 of raw balance. Kapag actually, pagka rectangular kasi, ang raw balance na gagamitin mo dito, yung formula diba? Ngayon, pag itong raw balance na ito, ginamit mo sa irregular section, mapagsak ka lang naman dito sa ESB muna. So, ito, this is a more general formula than this one. Okay. Ganun yan. Ngayon, may makikita kayo dito yung iba, ito ang ginagamit na kasi parehas lang naman yun yung may itong formula na ito, pwede rin yan, parehas lang naman yung lalabas na value, pwede rin yan, makikita nyo yung iba gumagamit yan, ito na rin, parehas lang yan. So this is for other members and this is for spiral. Ibig sabihin, pwede ito sa beams as well as sa tied columns. So ngayon, huwag niyo munang isipin yung mga type codes. Yun pwede nun ito na value na 5 threads. Okay. At saka yun yung C over DT. Okay. C over DT. Ngayon, explain ko lang kung bakit DT nilalagay natin. So ngayon, kung sabihin natin kung one layer, C over D na lang ito. C over D. So ang tinutukoy ko kasi dito sa DT na ito, halimbawa meron tayo beam dun na alam natin na magdi-design tayo. Kasi alam natin sa laki na niya ng reinforcement tayo, kaya sa dami ng reinforcement na gagamitin natin, pwedeng maging 2 layers yan. So pag naging 2 layers yan, ito yung pinaka-DT natin, itong pinaka-malayo. From the compression phase to the tensile bar, ito yung DT. Ito yung DT. Ang D, hindi ito ang D. Ang D actually is galing dito sa centroid, sa CG. Okay? Yan ang ibig sabihin. Kaya sa definition ng D natin, di ba? From the centroid of the reinforcing units. Now, ito na naman yung ano natin. Okay, sinabi ko na ito. This is just being repeated. Balance strain, again, formula. So, what else? Doon na tayo sa lesson 2.1. Okay? So, magdi-design na tayo. But, doon na tayo sa next video. Okay?